And there's three different types of van der Waals forces. And so let's start with the weakest of all of them. It's called London dispersion force. Sometimes they're just called dispersion forces. Thank you. Take care. And this, how do you tell if a compound has London dispersion forces? Well, all of them do. All molecules, all covalent compounds will have this London dispersion force. But when we're talking about intermolecular forces and properties, the stronger intermolecular forces will determine the properties more so than the weaker ones. So in general, we're going to talk about, okay, what's the dominant or predominant intermolecular force we're dealing with? So all covalent compounds will have the London dispersion force. But for its predominant force, if the predominant force is London dispersion, then it's for nonpolar molecules. So let me just say this is the weakest. So for example, if we have H2, N2, O2, F2, Cl2, Br2, and I2, these are the diatomic molecules. Are they polar or nonpolar molecules? Nonpolar. Do we all remember how to do this? How to determine if a compound is polar versus nonpolar?
Electronegativity and
symmetry. We find the difference in electronegativity between the bonds, determine partial positive, partial negatives, and if we can draw a line that separates the positives from the negatives, then it's polar. If we can't, it's nonpolar. And we'll go through some more examples just to make sure we got this.
So the diatomic molecules are an example of...
Yeah, these are examples because they're all nonpolar. But what about CH4? Is that a polar or nonpolar molecule? That's also nonpolar. Therefore, its predominant intermolecular force between methane particles is going to be London dispersion. And it's a weak force. And if you think about methane, well, it's a gas, right? So it's going to be relatively weak for that one anyway. Okay, so what about properties? What properties does this help us to determine? And it is the melting point and boiling point. In fact, all intermolecular forces determine this, not just London dispersion. But if all of these molecules have London dispersion forces, are we going to say they all have the same melting point, boiling point? How do we order? And we need to know this for the exam, how we order by increasing melting point or boiling point. And it has the same relationship. But as we get a larger compound, it's going to have a higher melting point or higher boiling point. The larger the compound, the higher melting point or boiling point. And that's kind of the way it's going to be for all of the properties we're going to deal with. The stronger the force, and if you think about this, let's just talk about boiling point for a minute. You have these molecules that are close together because they're in liquid form. They're held together, and then you heat it. What happens? It breaks them apart, turns them into gas, right? Well, they can't break apart well, they can, but they're going to have a harder time breaking apart if they have a strong intermolecular force. Does that make sense? So if they're held together tightly, the molecules, I'm not talking about the bonds, I'm talking about this intermolecular force. If they're held together tightly, or the tighter they're held together, the more energy it's going to require to get them to come apart and form gas, right? Same thing with melting point, going from solid to liquid. Solid, they're a little bit more structured, and then you give it energy, and then it melts it. Kind of doesn't break it apart, but it kind of separates it a little bit, and they can flow. You with me?
So when you specify larger the compound, are you referring to molecular mass?
Yep. Molar mass. It also is determined by the structure and the shape and even the size. But if it has a bigger molecular mass, molar mass, those other things are also going to be. So that's the easiest way for us to determine. So if we put these, forget about methane right now, which one has the lowest melting point based off of what we just talked about? H2, because has a molar mass of about 2, right? Nitrogen has a molar mass of 28, 32, 38, about 71, about 160, and about 254. Okay? My numbers might be slightly off, but we can see that the molar mass increases, then so does the melting point or the boiling point. So if we put these in order of melting point, boiling point, then this is what it would be. Now I wrote them in this order on purpose, but on the exam they might be in different orders and you'll have to put them in order. Does that make sense? Okay. Should we try one more? That one is pretty straightforward. In fact, I think if they all have the same intermolecular force, they're all pretty straightforward. So let's say we have GeH4, CH4, SiH4, and SnH4. Now, what do you notice? A pattern. You see a pattern here? They all have 4 hydrogens. So do we have to worry about the 4 hydrogens? No, that part's the same. So which one has the lowest molar mass? You look at your... Yeah, carbon's going to have the lowest, so that's going to be the lowest melting point or lowest boiling point. And then which one after that?
Is it melting point or boiling point or both?
Both.
Okay.
But generally you talk about one at a time, right?
Okay.
So if we want to compare, okay, the order of increasing melting point, and then we want to compare the increasing of boiling point, they're going to be the same, right? Because they're both dependent on, first of all, the first thing we got to look at is what type of intermolecular force. But if they're all the same intermolecular force, then we have to check, what about their masses? So look at your periodic table. Which one has the next least mass? Silicon, right? And then germanium. And lastly, antimony. Or tin. That's not antimony, that's tin. Does that make sense to everybody? so now what about, we're gonna talk about something that we learned in organic chemistry, and we do a lot of it in organic chemistry. We're just gonna do a little bit of it, yeah.
So I understand the molecular weights referring to melting point and boiling point.
Uh-huh.
How does this relate to the London dispersion forces? Is that just identifying non-polar
Okay,
molecules?
great question. So so there are 3 different types of intermolecular forces we're going to talk about. London dispersion is the weakest out of all 3 of them. And so if we have a London dispersion, one molecule has the intermolecular force of London dispersion, another one is hydrogen bonding. Well, which one is going to have, so if hydrogen bonding is stronger, which one is going to have a lower melting point? The weaker one or the stronger one? The weaker is going to have a lower melting point. It's going to take less energy to break those apart. Does that make sense? Let's do another example. So in fact, I don't want to do another example.
Makes sense. I guess I just can't articulate what the heck the London dispersion force is.
London dispersion forces
Other than
are,
that it's
are present in non-polar molecules. So if we have, for example, we have H, that's our hydrogen molecule. Well, there's going to be more HH molecules around, right? And so there's going to be an intermolecular force that kind of holds these together. And this intermolecular force is called the London dispersion force. It's the intermolecular force that holds the non-polar molecules together. And this is the weakest. And we'll get into the other ones. Did that answer your question?
Yes.
Thanks for asking. Okay, another term is isomer. This is not an intermolecular force, this is just a new term. An isomer is a molecule with the same molecular formula, but they're arranged differently. So, a molecule with the same chemical formula, but arranged differently. So for example, we could have C5H12. We can have it arranged where there's a carbon in the center, a carbon on the outside, and then all your H's are right here. And in organic chemistry, we don't write those H's, we don't even write the C's, we just draw kind of a structure that way. So that's the structure of what we call neopentane. You don't have to know the name. And then another C5H12 might be isopentane. Again, you don't need to know the names. Going to be something like that. And again, we have a lot of carbons hooked, or hydrogens hooked to this. And then pentane is going to look something like this. So this one, they all have the same molar mass. So what about increasing melting point or boiling point for these? They are slightly different, not a whole lot different, because they do have the same mass. So another thing that affects melting point, boiling point is, yeah?
Did we learn about this when we spoke about Lewis structures?
A little bit. We didn't call them isomers, but that's what, these are all isomers because they're the same number of atoms of each element. They're just structured a little bit different. So this is the smallest area or surface area. And it's kind of hard to tell just by looking at my stick figures. And this one right here is the largest. Since it has a larger surface area, that's kind of like the size, the bigness of it. And so this is going to have a higher boiling point. And so, for example, and again, you don't have to know this, the boiling point of this one is 36 degrees. The boiling point of the center one is 27 degrees. And the boiling point of this one over here is 9.5 degrees Celsius. So as they get larger, also has a stronger or a higher melting point or boiling point. So not just molar mass, but size, structure, okay? Yeah.
What determines the arrangement?
You'll learn that in organic chemistry. We're not going to discuss that. So that means I won't ask you a question about that. Sound good?
Sounds good.
Okay. Now let's talk about why that is. So if there's hydrogens hooked to these, I'm not going to draw them all, right? But it has more places that it can have the intermolecular forces attracted to it. So there's more forces, more number of forces altogether. Therefore, it's harder to break apart. Does that make sense? When it's over here, you only have 1, 2, 3, 4 points with 4 other points. This one has 5 points. And right over here, you have 1, 2, 3 points. This one right here can't really, it's kind of right smack in the middle, so it's in the way of things. You can have a harder time with that intermolecular force. Does that kind of make sense? Why a bigger surface area makes, or a different structure makes a higher or lower melting point? How are we feeling? Good? And so far, these ones that we're talking about, these are all nonpolar molecules. So this is just London dispersion force. But the same thing applies to all of the other types of intermolecular forces. So let's go on to the dipole-dipole intermolecular force. So this dipole-dipole interaction is much stronger than the London dispersion, but it's weaker than the covalent bond itself. So the bond holding the hydrogen with the chlorine, for example, this bond, you're not going to break it. I mean, you can. You're not going to break it just by giving it energy, okay? But so if we have another one of these, you're going to have this intermolecular force, which is a dipole-dipole intermolecular force. And we'll talk about why it is in just a minute. But that dipole-dipole attraction is much, much weaker than the covalent bond itself. That applies to all of the intermolecular forces we're dealing with, not just London dispersion, not just dipole-dipole, but all of them, okay? So dipole-dipole is between polar molecules. So if our molecule is a polar molecule, then it's going to have dipole-dipole interaction. Good? And so now if I say, okay, if I have CH4 and CH2Cl2, which one has a higher melting point? Would be a good test question.
CH2Cl2?
Why? You don't even have to worry about the mass here,
More bonds.
because this one is a polar molecule. This one is nonpolar. So what intermolecular force are holding these ones together? The carbon and the hydrogens? That's the London dispersion force. Which one's holding the CH2Cl2 together? That's the dipole-dipole. And a dipole-dipole is stronger than a London dispersion force. Therefore, it's going to take more heat to get it to break them apart and get it to boil or melt. So talking about melting point or boiling point, then the one with the dipole-dipole interaction is greater. And you don't have to worry about the mass. You only worry about the mass if they have the same intermolecular forces. Make sense?
So what was the question? Which one is stronger?
Which one has a higher melting point or higher boiling point? Are we doing okay? Making sense?
So is it a dipole-dipole force?
Dipole-dipole intermolecular force. Yep. So this is also an intermolecular force. It's between the molecules. So it's not a bond. It's just an attraction between the partial positive, partial negative. And for nonpolar molecules, partial positive, partial negatives are tiny, 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 if any, right? Yeah.
So that less than sign, is that saying that CH4 has a lower boiling point?
Yes.
Okay.
Yeah, that's what I'm saying there. Uh-huh. So the stronger the intermolecular force, the higher melting point. The stronger intermolecular force, the higher boiling point. If they're the same intermolecular forces, same type, then you have to check the mass. Then you have to check the size of the structure. Okay, okay, the last type of van der Waals forces or intermolecular forces we're talking about is hydrogen bonding. And this is the strongest out of the three. And these are also between polar molecules. So now here's where they're different. Specifically, we have a hydrogen-nitrogen bond, a hydrogen-oxygen bond, and a hydrogen-fluorine bond. If we have a compound where hydrogen is directly bonded to either nitrogen, oxygen, or fluorine, then the intermolecular force that is between those molecules is going to be hydrogen bonding. It's not a bond. It's still an intermolecular force. But that's how you tell the difference between a dipole-dipole and a hydrogen bonding. So technically, they're both dipole-dipole. We have a special name for hydrogen bonding because it's a little bit stronger, and it happens in our body.
If it's polar and contains hydrogen.
Not contains hydrogen. Hydrogen has to be directly bonded to nitrogen, oxygen, and fluorine. Why those three? Higher electronegativity. Yeah, they're the highest in electronegativity. I know chlorine has the same as nitrogen, but But why do we have a special one for these? Because they're in our body. So these are the forces, the intermolecular forces that holds DNA together. So let me see if I have an image that I can show you. So this is not a biology class, and I'm not gonna have you memorize these things, okay? But, and I don't even know if I can pronounce all these names, but we can see the intermolecular forces right here. So these right here are the intermolecular forces that's holding these components together. I couldn't tell you what these are, guys. This is not my field of expertise. I couldn't. But it's in DNA. It's what's holding these guys together right here. Okay? These hydrogen bonding intermolecular forces. Good? So that's why we have a special name for hydrogen bonding, even though they're still dipole-dipole. And what causes the dipole-dipole? We kind of talked about it when we talked about a polar molecule. If we have water, for example, we have the partial negative here, the partial positive, and we have this dipole right here. Remember talking about these vectors? Yeah, this is a dipole. And when you have two dipoles that are opposites and they attract each other, that's a dipole-dipole interaction. We just have a special name for ones that are bonded, hydrogens bonded directly to nitrogen, oxygen, and fluorine. Any questions on the three intermolecular forces? Yeah.
Before you were saying that the larger the compound, in terms of molar mass, the higher melting point or boiling point.
Uh-huh.
But wouldn't, for like the isomers you gave the example of, wouldn't they all have the same molar mass? They just have a
They
larger
do.
surface area.
But there's a larger surface area.
Okay.
So it's not just dependent on the mass, but the size of the structure. Uh-huh.
Okay.
Surface area. All right, let's do a bigger example. So let's say we have NH3, C3H8, and HCl. Let's order these from lowest to highest melting point, or lowest to highest boiling point. It's the same. First thing we do is determine type of intermolecular force. IMF, intermolecular force. We good? So let's determine that first thing. Don't worry about mass yet. Let's just determine this. What's the intermolecular force for NH3? Hydrogen bonding, because hydrogen is directly bonded to nitrogen. It is a polar molecule. What about C3H8? Is that a polar molecule or a non-polar molecule? Non-polar. How do you know right away?
They're super close.
Carbon, hydrogen, bonds. That's it. Do you remember that? If a compound only has carbon-hydrogen bond, it's non-polar. Because if you think about what's the carbon-carbon difference in electronegativity? 0. That's not polar. What about carbon-hydrogen? 0.4. That's pretty low, right? There is a difference, and it has a slight dipole. That's why it has London dispersion force. So this is non-polar. This is London dispersion. Make sense? And then HCl, that's dipole-dipole. Because it is a polar molecule. Dipole. Is it hydrogen bonding? No, because hydrogen is not bonded directly to nitrogen, oxygen, or fluorine. So don't just look at, oh, if it has a hydrogen, then it's hydrogen bonding. Because these all have hydrogen in it. Okay? So if we put these in order from lowest to highest, what would it be? C3H8 is the lowest, then HCl, and NH3 is the highest because it has a stronger intermolecular force. And if you're doing this and a couple of them have the same intermolecular force, now what do we do? Yeah. Determine the molar mass. Whatever one has a higher molar mass has a higher boiling point, higher melting point. Good? Would you like to, oh, I didn't give you guys practice. Sorry about that. Busy when everybody came in. Have it out. Do you want to practice another one right now? Maybe we could just determine what type of intermolecular force it is. So let's do CO, carbon monoxide. So to determine the type of intermolecular force, we got to first determine what? Yeah, if it's polar or nonpolar. To do that, we draw the Lewis structure. We determine the molecular geometry, right? Determine if the bond is polar or nonpolar. Draw a straight line that separates the partial positives from the partial negatives. Can anybody tell me if this is a polar or nonpolar molecule? Should we just try it from scratch? Go start from the bottom? Okay, we got to draw the Lewis structure. Do you remember how to do that? Count the valence electrons. There's 4 here, there's 6 here. That's a total of 10 electrons. Which one's central? Carbon is central. In this case, it doesn't matter because there's just 2 atoms. So there they are. We have 2, so we have 8 left. Where does the rest go? Which one first? The non-central first. Because the central is the lower in electronegativity. So the higher in electronegativity is going to take those electrons first, right? So 2, 4, 6, that has an octet. We have 2 more, so it's going to go around that carbon. And again, this is not the only way to draw Lewis structures. This is just the way I taught you. Okay? Now let's make sure they all have an octet. So what do? Move them from oxygen to make a double or triple bond, right? So there's the structure for carbon monoxide. What's the molecular geometry here? If carbon's the central atom, there's 2 regions of electrons. So what's the molecular shape? Linear, good. It is linear. So it's already written that way. That's good. So let's find. There's only one bond. It's a carbon-oxygen bond. What's the difference in electronegativity? This has electronegativity of 3.5, and this is 2.5. Has a difference of 1, so is it polar or non-polar? Polar. Therefore, which one is partial negative? The oxygen. Do we remember this, or is it just way a long time ago and we forgot it all? Uh-oh.
Without my cheat sheet, I have no idea.
Uh-oh. But you can do it with your reference sheet? Okay. Need to. So we can draw a line that separates the positive from the negative. So that means this molecule is polar. Okay. Now we know it's a polar molecule. So what are the 2 options of intermolecular forces? Hydrogen bonding or dipole-dipole. Which is it? Oh, there's no hydrogen in it, period. So yeah, this is dipole-dipole. Good? Do you want to try another one? Seeing no's? Any, okay, let's, if you have this sheet, you can tell me which one you want to do, because I'm just picking, let's pick CH2F2. Does this look like hydrogen bonding or not? Why not? There's a fluorine and there's a hydrogen in there.
The carbon is central.
The carbon is essential. That's why I have to know the structure, right? It's going to look like this. Is there a hydrogen bonded directly to fluorine? No, so this is not hydrogen bonding, even if it's dipole, or sorry, even if it's polar, right? First of all, is it polar? How do we know? We got to know the molecular geometry. It's going to look something like this, right? Do I need to go through of how I know that? There's 4 regions around the central atom. No lone pairs, so this is tetrahedral. Then we look at the carbon-hydrogen bond is nonpolar, so we don't have to worry about positive negatives, right? Carbon-fluorine, this is partial negative, this is partial positive. We draw a line that separates the positives from the negatives? Yes. Therefore, this is polar, so what type of intermolecular force does it have? Dipole-dipole. Good? Do you want to do any more? No? Okay.
Can I ask a question?
Yes, you can.
Can we do the CH3CH2OH? 'Cause, I mean, the OH would be a hydrogen bond, right?
Uh-huh.
But the rest of them wouldn't.
That's right. CH3CH2OH. So if I give you a huge molecule like this, I will give it to you as the structure. So I'm not going to ever give it to you like this. That requires you to know organic chemistry, and I'm not going to have you do that, because then we can draw different isomers of the same things. Like, okay, which one is it, right? I'm not going to have you do that in this class. If you want to do that, you take organic chemistry. Sound good? Okay. So this is how it's structured. We got the 3 hydrogens there, 2 hydrogens there, oxygen and a hydrogen. So that's the structure. I didn't draw the hydrogens, but you follow? Okay. So let's see. These are going to be nonpolar, right? All carbon hydrogens, they're nonpolar. So we got to check this bond and this bond. Are they polar? Look at your electronegativity chart.
The hydrogen-oxygen bond is.
Which one's partial negative?
Oxygen.
What about the carbon-oxygen bond? Oh, we just did it.
That's also.
This is partial positive. Doesn't look like you can separate it, does it? Why can't we? Because this is just the Lewis structure. We have to know the molecular geometry. If we just want to center it around oxygen, because this is nonpolar, so we don't have to worry about that, right? So oxygen with 2 lone pairs, something like that. Partial positive, partial negative. This is a bent molecule. We can separate the positives from the negatives. This is a polar molecule, so what is it? Dipole or hydrogen bonding?
Hydrogen?
Or both?
Well, technically it's both.
It has both, but which one is the dominant?
The hydrogen bond.
Hydrogen bonding. On the test, it's going to say we have this molecule and this molecule. In fact, let's do them like that. So if we have CH3OH, for example, and we have H2O, what intermolecular forces are between these two?
Hydrogen bond.
We have hydrogen bonding. We have dipole-dipole. And all molecules have London dispersion. So the one between the carbon and the oxygen, that's the dipole-dipole, right?
So you're saying this example, there's all three intermolecular forces?
There is. It does have all three of them, and I think there's at least one test question that says, what are the types of intermolecular forces associated with these two molecules? And so that would be my answer.
We're looking at them individually, right?
Mm,
Independently?
no,
Or is it how
how they're,
CH3OH connects to H2O?
yeah, how they're connected. So here we have, we're gonna have HOH, there's gonna be that bond right there, right? That intermolecular force. There's a different color for that. And then we're gonna have, oh, we could have also the H from this guy, right? Also hydrogen bonding, because H to the oxygen. Well, the H to the oxygen is that. And so there's hydrogen bonding there. And then you have, let's do a different color here. You're gonna have a dipole-dipole interaction right there. But then you have all these other hydrogens. Could you have another, something over here, let's say, another carbon, oxygen, hydrogen here? Oh, we could have another interaction right there. That's the London dispersion force. Does that make sense? You're not going to have to be able to draw that, guys. You won't. You just have to know what type of intermolecular forces exist. Now the question might say, what is the predominant intermolecular force? In other words, which one is the strongest? Hydrogen bonding, right? That's the one that's going to take precedent over this thing. Yeah.
Can we do a quick, steps to solve
To solve,
the intermolecular forces?
so to determine the intermolecular force?
Yeah, of the molecule.
Okay. So let's just summarize it here. All molecules will have London dispersion. All of them. Did I suppose? All of them do. Okay. And what's the predominant one for nonpolar molecules?
Hydrogen?
No, for nonpolar molecules,
Sorry.
is the predominant one for London dispersion. or London dispersion is the predominant intermolecular force for nonpolar molecules. Good? So steps on how to determine intermolecular force. Step 1. What do we do? Determine if polar or not. If it's not polar, what does it have? London dispersion. If it is polar, we got to check one more thing. What do we check? If hydrogen is directly bonded to nitrogen, oxygen, or fluorine. If it is, it's hydrogen bonding. If it's not, it's dipole-dipole. Good? How we feeling? Is that what you was asking?
Well, I was asking us to like just do like a Barney style breakdown, like then Lewis structure, then molecular geometry, and then dipole, like steps.
So yeah, how do we determine if it's polar? We draw the Lewis structure.
Right.
How do we then? Is that all we have to do? No, we got to determine the molecular geometry. And then we do the straight line test. Yeah, same thing we learned a while back, right? But we're going into this assuming that we know how to do that. Do we need extra practice? If we do, then get it. I'm just kidding. We can do more if you'd like. Are we good? And we're just going to have to do more practice to make sure we are good. Okay? Let's talk about another property. So one property, we talked about two properties already. The first one is melting point, second one is boiling point. They kind of follow the same process, right? The stronger the molecular force, the stronger the boiling point. The stronger the molecular force, the stronger the melting point. Okay. Now let's talk about another physical property that we're going to run into. Viscosity. Anybody know what that is? The resistance to flow. So this is for liquids. It's the resistance to flow. I guess it could be for gases too, but we usually don't say a gas is viscous, right? So what's a viscous material that we know of? Molasses, honey, oil. Is water viscous? Yeah, but it's a lower viscosity, right? You jump in the water, it slows you down. It does have resistance to flow, but compared to oil and honey and molasses, it's a lot lower, right? So what does that tell you? What has a lower, if we have oil versus water, which one? Hold on a second. That's not right in my mind. Okay, hold on. There's a flaw in my notes. Whoa. That's not cool. I'm gonna have to get back to you on this one, because that one doesn't make sense in my mind now. Because in my notes it says the higher the viscosity means the higher the intermolecular force, but that's not true in this case. Because this oil is a nonpolar molecule, right? That's London dispersion. Water is hydrogen bonding. And oil is more viscous than water. Yeah.
Do they have higher viscosity among the same intermolecular forces? That would-
Yeah, but it still wouldn't follow.
Because hydrogen, the water is so much smaller molecular.
That shouldn't be. So when we check the properties, then the one with the higher intermolecular force has the higher property. Let's see. Yeah, check ChatGPT. Huh. Yeah. I'm glad we come up to that stop, so I don't feed you lies. Let's move on. I'll look that up and come back to it, unless Evan's got it right there. Huh. Yeah, let's move on, and I'll get back to that. All right, surface tension. You guys know what surface tension is? So it's the ability to walk on water, right? Oh, wait. But water has a pretty high surface tension. In fact, let me show you an example here. You guys ever floated a paperclip or a staple on some water? You can. Same thing with a hamster or gerbil water feeder. You guys know how those work? All they have to do is touch that little stout coming out, and it lets water come out, right? Why doesn't water come out all the time? Because there's a little bit of space between the little ball in there, the stout, and so the water has a strong enough surface tension that it'll hold it there. You can take one of those bottling jars, you know what I'm talking about, and you put a screen over it, and you put the lid on. You fill it with water through the screen. Then you put something on top of it, lift it upside down, and take the paper away from it, and no water comes out. Because there's such a small space between those screens, there's enough surface tension in the water to hold the weight of all the water from coming out. Same thing here. There's just a small space between those wires, so water will just hold it there. Now, if you just drop it in, it's not going to hold it, but you have to set it in real gently, and then it'll hold it. Okay, so that's what surface tension is. And surface tension is why we can have bubbles. Kind of holding all that together. Good?
I think I figured it out.
Yeah, what does it say?
So it says, you might find it surprising that oil, which relies on London dispersion forces, is more viscous than water. It says that water has hydrogen bonds, which is stronger. It says, sorry, says that basically since oil is a larger, more complex molecule.
Has more
it's
surface
lighter,
area.
heavy, and elongated, which creates a more surface area for a stronger cumulative London force. So if you accumulate all the London forces, I guess, it becomes like.
Okay,
stronger.
that kind of makes sense. What I was talking about,
It's kind of an exception, it's saying. Like,
yeah.
exception to like.
So when I talked about the
it's
surface
not
area
simple.
somewhere, right here, we got a lot of these different points of London dispersion. In oil, it's really long. It's a huge chain of carbon-hydrogen bonds. And you got all those different points, all those different London dispersion forces that kind of hold it together more. So that in turn makes it stronger than water would be, because water is just a small little guy. Okay, that makes sense.
Yeah.
So in general, the example that I picked out of my head was not a good example. So in general, the higher the intermolecular force refers to higher viscosity. Kind of like the same thing with melting point and boiling point. The higher the intermolecular force, the higher the melting point, boiling point. Do you think there might be some exceptions there too? Yeah, maybe, right? So I just picked one of the exceptions. Same thing with surface tension. As the intermolecular force increases, so does the surface tension. But this surface tension is a common property of hydrogen bonding. Since it has a higher intermolecular force, it's going to have that surface tension. And this is also for liquids. You won't have it for gases. And then another property of hydrogen bonding. Any questions so far? Hey, thanks for looking that up, Evan. Any questions on that? So they all kind of have the same relationship. As you have a strong intermolecular force, it's going to be harder to pull it apart, right? It's going to hold together more. It's going to stay as a liquid or stay as a solid a little bit more.
What's less viscous than water?
Alcohol. I mean, alcohol has water in it, but if you take, the more pure it is, it's going to be less viscous. Or hexane, which is a carbon-hydrogen bond of 6 carbons. It's more volatile so volatility, we'll get to that in a minute. It's kind of, that one has an opposite effect. The higher intermolecular force, the lower volatile it is. But we'll get to that. Okay, the next property I want to talk about for hydrogen bonding is capillarity. Anybody ever do welding or soldering? Okay, you get some copper pipes and you hook them together. You heat it up, put some flux in there. You heat it up and you put some solder next to it, and it'll just suck that solder right in between the two pipes. Because it's a small space, and so that is called the capillary action. And let me kind of demonstrate, or kind of try to explain what this is. So in surface tension, you have a cohesion force, where the molecules are attracted to one another, make that surface tension. In capillarity, you have an adhesion force where this water is attracted to the non-water, which is the side of the material of the container here. So let me show you another picture that shows a little bit. You guys ever use a test tube in lab? And you get this, we call the meniscus. Why does it do that? Because of the adhesion between the water and the material of the test tube. It kind of climbs up the walls a little bit, goes against gravity. As you make that tube more narrow and narrow, then it actually climbs up it. And if you ever, so in medical they have these little capillary tubes that they kind of, when I get my A1C every 3 or 6 months for my diabetes, then they have this little capillary tube and they just suck a little bit of blood up that tube. They don't have to do anything, they just have to touch it to it and it just kind of sucks it up. It's the same way plants get their water from the ground. Have these little narrow, like a flower has a narrow stem, it just sucks it right up into the flower. But that's capillarity, or the capillary action that causes it to pull up, go against gravity. So the more dense it is, the less it's going to go up, obviously, or I hope that's obvious. It's harder to go up against it, but if it's less dense, it's going to go up even more. That kind of makes sense? So that is a property of hydrogen bonding as well. But here you have mercury, liquid mercury, kind of goes the other way around, because that cohesion force is stronger than the adhesion force. Good?
Can you define adhesion?
So cohesion, good, let's talk about this. No, thank you. Cohesion is attraction between same molecules. So in surface tension, you have those same molecules attracted together, causes that to allow the paperclip to rest on it. And adhesion is the attraction between different molecules. So like on the test tube versus the liquid inside of it, that's why it climbs up the wall, it adheres to the wall.
Is surface tension a property of just hydrogen bonding?
I think so. Because it's a stronger intermolecular force, and you need that stronger attraction to be able to have it. So I believe it is. Now, are there examples where it doesn't? I don't know.
So what is the definition of capillarity?
Capillarity is, well, it has that adhesion force, so it's the ability to climb up the walls of, so that's why it makes the meniscus. That's not a great definition, but the ability of a liquid to flow up small tube against gravity. Do you care if I summarize the intermolecular forces before we go on a break? And then we can take a break and then talk about something different.
Yeah.
Okay, so in summary, if we have strength of intermolecular force going up, then we have hydrogen bonding on top. And hydrogen bonding is between polar molecules, specifically hydrogen is bonded directly to nitrogen, hydrogen to oxygen, or hydrogen to fluorine. Then you got the next one is dipole-dipole. And this is between all other polar molecules. And London dispersion is the weakest. And that's between nonpolar molecules. So we can also say, as we go up in strength, then we have higher melting point / boiling point. We have higher viscosity in general. We have higher surface tension and capillarity. They kind of all have the same trend. Does that make sense? Okay. So first thing we do is we check type of intermolecular force. And then all of these properties, hydrogen bonding is greater than dipole-dipole, which is greater than London dispersion. If they have the same intermolecular force, in fact, well, let me say this. What about NH3 versus H2O? Which one's greater? You could do it with weight, and it would do the same thing, but the attraction between, or the difference in electronegativity between hydrogen and oxygen is higher than nitrogen and hydrogen. But if we have HF, that one's higher, but there's only one bond. This structure would be greater, so it would be H2O. So if we put it in order from lowest to highest, it'd be HF, then NH3, then H2O. And that's because of the structure.
Is that because they're so close to the same mass and there's more bonds?
There's more bonds. There's 2 here, 3 here, but since there's a lone pair right there, it's, yeah, this just has 1 bond, so it's gonna be lower.
So what if it was like, hydrogen to iodine, like a significantly heavier molar mass?
Then these ones are still gonna be higher. Why is that?
Is it because the number of
Because it's
bonds?
not hydrogen bonding.
Oh, sorry. Oh, so we're talking
'Cause-
about specifically hydrogen bonds?
Well, yeah, if they're all 3 of these are hydrogen bonding, because it's nitrogen, oxygen, and fluorine,
Okay.
directly bonded to hydrogen.
So this is specific to hydrogen bonds that we're talking about?
Well, if they all have the same intermolecular force, you have to check other things,
Right.
right? So if it's hydrogen bonding, you check, okay, which one is higher electronegativity difference, but also the structure, the amount of points that it can hook to, that the hydrogen bonding can occur to. Because the HF just has 1, 2 points. H2O has 1, 2, 3 points. NH3 has 3 points, but because oxygen is more favorable to attract another hydrogen there, it's going to have those extra 2 points. And nitrogen has these 3, but it's not as favorable for that one. Yeah.
So you're basically like checking how big the structure is.
That, yeah. So there's a few things you got to check for mass.
Or
And-
like, what are you checking with this?
The surface area, the structure,
Okay,
yeah.
So, okay.
Yep.
So that would, it would be like check type of IMS, and then if they were all the same, then check
Check the structure,
structure.
check the mass would be a good place to start. The molar mass. But specifically for hydrogen bonding, then you would check those things.
So if it was just dipole, we don't have to worry about the amount of bonds, it would just be whatever's heavier.
Yeah.
Okay.
For the most part, yeah. And then, so molar mass, increasing molar mass increases in property. We got the size, larger size increases property. Like we dealt with oil and water. And then, of course, polarity. So if you have even dipole, if you have one molecule that's you got 2 molecules that are dipole, but one of them has a stronger difference in electronegativity, that one's going to have a stronger the higher property. Does that make sense? Just trying to think of on the exam. There will be one with structure. There's going to be the mass differences on there. But I think the main question that you'll get on the exam is, what type of intermolecular force is predominant? I saw a lot of questions like that on the exam. Yeah.
What is INC property? Increases?
Increases, yeah, sorry. So it increases the surface tension, it increases the viscosity, it increases the melting point, boiling point. We good? Okay, should we finally take a break? Sorry, that was a long time. 10 minutes, I guess.
You, is it gonna be pretty conductivity and the bonds and the structure and the surface area of the structure and the molar mass. Like, if we're checking all these things, is it gonna be like, oh, this is clearly like the strongest, or, cause what I'm worried about is I'm gonna be in the test and I'm gonna be like, well, this has a stronger, like a bigger molar mass, but this has a different structure, and like,
So
how do you
I
know?
I think on the exam, I give you one specifically, and I even draw out the structures for you.
Okay,
So, okay, which one has a greater IMF or greater melting point or great, you know?
so if we know these things, it should be pretty clear.
Yeah.
Okay.
But for the most part, if they have the same intermolecular force, you can check their masses. But, like, yeah. I don't think, I went through them all and I don't remember of some that are like, oh, come on, that's tricky. I don't remember of them, so
Okay.
I hope not.
Okay.
Okay. All right. Any questions on intermolecular forces before we move on to phase changes? All right. Phase changes, that sounds pretty simple, right? All right. A little bit more into it than just melting stuff. Okay. So vaporization. This changes from what to what? Yeah, liquid vaporizes, turns into a gas, right? So this is the phase change. From liquid to a gas. So the vapor pressure depends on intermolecular forces. So let's try to make sense of this. So if we have two liquids, one has a higher intermolecular force, which one is going to vaporize easier? The one that has a lower intermolecular force, right? It's just like boiling point, right? Vaporization is basically the boiling point, kind of, right? Well, not exactly, but so if it has a higher intermolecular forces, it's going to have a higher vapor pressure. We good? And vapor pressure is directly related to volatility. So if something has a high vapor pressure, is it more volatile or lower volatility? More volatile, right? Directly related. That's on the test, actually, yeah.
Does that seem directly proportional?
Yes. So, volatility. The volatility is directly proportional to the vapor pressure. Oh, hold on a sec. My No, I wrote that wrong with the higher intermolecular force. So if you have a strong intermolecular force, yeah, that's right, that's right.
So it's like
Sorry, it's just a wording. So higher intermolecular force, it's gonna be harder to vaporize. Yeah, that's right, okay? So know this for the test. That's an exact question on there, okay? If we have a higher boiling point, that means we have a higher or lower vapor pressure. Higher vapor pressure, okay? Next phase change is condensation. Condensation is phase from what to what? From gas to liquid is the opposite, right? Think about condensation on your drink, right? So it's the water in the air that cools and turns into liquid water. So in a closed container, then the rate of vaporization equals the rate of condensation. So think about, here's your container, soda pop container or whatever, right? You have your soda in there, and you have your carbon dioxide coming out, but you also have carbon dioxide going in. And the rate at which it's going in and out is the same. So as long as you keep that sealed, it's gonna stay the same carbonation, right? Then you open it and you drink it, it's still pretty strong carbonation, right? When you open it, now what's gonna happen? That carbon dioxide's gonna go out more than it's gonna go in. Make sense? Gotta make sure I'm telling you right on this next thing, sorry. Oh, okay. All right, so that's talking about, no, hold on. Sorry, guys. Sorry, I can't get past that. All right, let's do an example. So let's I think I told you wrong on vapor pressure. I did. Dang it. Sorry, guys. So let's write this. So as the intermolecular force increases, vapor pressure decreases. Okay, so
Inversely proportional?
they are inversely related. Now, when I was thinking about this earlier, I was thinking boiling point, that's not the same thing. So vapor pressure, if we have, so think about if we're at sea level, you have all this pressure on top of the pot of water you're gonna boil, right? So you have all this pressure on there. When is it gonna boil? It needs more temperature to boil, right? So you get this higher vapor pressure. It's gonna take longer to boil. If you go up in the mountains, you have less pressure, and it's gonna boil a lot earlier. Like the boiling point in this room right now is like 98 degrees Celsius. And at sea level, it's 100 degrees Celsius, right? So that's a difference between boiling point and vapor pressure. So yeah, go ahead.
But so volatility is still directly proportional
So
to
if
vapor
it's,
pressure.
Yes,
So both vapor pressure and volatility are inversely proportional.
yes,
to time. That
yes.
makes sense.
So if you think about, so for this example, if we have water, I'm going to draw these structures because we won't know what they are if I don't. So here's water. We know that one. Then we have diethyl ether. And those carbons have hydrogens bonded to it. You guys okay with me not writing the bonds? Okay. And then we have ethanol. So this is hydrogen bonding, this is hydrogen bonding, and this is just dipole-dipole. You with me? And so water has the highest intermolecular force. That means it has the lowest vapor pressure and it's the lowest volatile. And that kind of makes sense if you're dealing with alcohol versus water, right? Alcohol is more volatile than water is. Yeah? And therefore, alcohol has a higher vapor pressure. Question? No? So water,
Can you explain it one more time?
yeah. So water is going to be, since water has the two hydrogens there, it's a stronger hydrogen bond than ethanol is. So ethanol, which is C2H6O, and diethyl ether, C4H10O. So this has a higher volatility or higher vapor pressure. And this has a lower pressure or lower volatility. So let's just think about alcohol. Let's take rubbing alcohol. We're all familiar with that. And you put it on your skin, what happens? It vaporizes. Right?
So, is that determined by the amount of hydrogen atoms? Like, what's an easy way to determine this?
Which one's greater out of these two? Or
Well,
all of
If we
them?
were to look at this and just like to just know in order from lowest to greatest pressure or volatility and
So
vapor pressure. how
as
would-
the intermolecular force increases, the vapor pressure goes down. They're inversely related. So this one right here is dipole-dipole. That means it has the weakest. That means it has the strongest vapor pressure. And it's more volatile than the other two.
Oh, sorry.
And then these two, since they're both hydrogen bonding, then we have to look at, all right, this one has two hydrogen bonds, and this one just has one. So it's gonna be easier for ethanol to vaporize.
Okay, so was the lower the intermolecular force, the higher the volatility?
Yeah.
Yeah, that would work too. Uh-huh. So if you, let me make sure I'm saying this correctly, because I'm messing you guys up today, am I? So, yeah,
Well, wouldn't the C2H6 be a 1:3 hydrogen to carbon ratio? So wouldn't there be more hydrogen bonds? to
there's
carbon?
0 hydrogen bonds. The hydrogens are right here. So this right here is a dipole-dipole interaction.
Right.
Because it's bent,
Okay.
so it's a polar molecule.
So we had to draw that, and we know that the oxygen is the central atom because it's hydrogen.
Yeah, and if I just gave you this as diethyl ether, you would have no idea, right? Because that's an organic chemical. So in the case of organic chemicals, I will give them to you. Okay, I'll give you that structure so you can make a better judgment on it. So let's see. If it has a stronger intermolecular force, it's gonna not go into gas phase as easy.
Right.
If it goes into gas phase easier, it has a lower intermolecular force, therefore it's gonna have a higher vaporization pressure, or vapor pressure. Does that make sense? Sorry for that flub up, guys.
So the vapor pressure is the pressure of the molecules, like, at least as it appears to.
Yeah, so if you have more gas particles, you're gonna have more pressure. So it's more volatile. That's why volatility is directly related to vapor pressure. Good? Sorry, I had it flipped in my head. Kind of had vapor pressure kind of matching boiling point for a second, but it's not the same thing. Are we good? I'm good now. Are you guys good? I'm sorry. Okay, now let's talk about an easier one.
Okay, now I keep on doing this, so can you go back, but can you just give me a definition of what vapor pressure is?
So vapor pressure, so think about this. If you have a container with something in it, and it's gonna vaporize just sitting there. And depending on what it is, it's gonna vaporize more. We say that's more volatile, right? And so if it's more volatile, then there's gonna be more liquid molecules that's gonna turn into gaseous molecules. More things gonna vaporize. And we're not adding heat here, we're not boiling, it just does it at room temperature. And the more of these things we have up here, there's gonna be more particles running into each other, therefore increasing the vapor pressure. Because there's more vapors up there. Does that make sense?
Mm-hmm.
Yeah.
So it's like the desire for a compound or molecule to just like naturally vaporize at a standard state.
Yeah. Yeah, it's not boiling point, and that's what I was kind of fighting in my head for a minute. Did that help?
Thank you.
Thank you. All right, melting point. Or melting is a phase change from what to what? Solid to liquid. And freezing is the opposite, liquid to solid. We all know those, I'm sure, right? I think we knew vaporization and condensation for the most part too. So when a solid is heated, then you're going to get a greater average kinetic energy, right? Does that make sense? We talked about the kinetic molecular theory. You have more kinetic energy. If you have more heat, more temperature, you're going to have a higher kinetic energy. And so if you have more energy, then this phase is going to, well, it's going to melt more, right? I'm just saying stuff we already know, guys. Sorry. One thing you do need to know here, this will be on the test. During phase change, temperature remains constant. So as you have a pot of water and you're trying to boil it, once you reach that boiling point, the temperature of that water will not change. And even though we continue to give it energy to keep boiling it, the temperature of that water is not going to change. It's going to stay 100 degrees Celsius or 98 at this elevation. It's going to stay at that boiling point until it's all vaporized. And if you continue to give it energy, now it'll increase temperature. Does that make sense? Same thing when you're freezing it. You have some water and you put it in the freezer. It's going to stay at 0 degrees. Once it starts freezing, it's going to stay at 0 degrees until it's all frozen. And then once it's all frozen and you keep it in the freezer, well, depending on what adjustment you put on the freezer, right? You put it lower, then it can drop even more. So during a phase change, the temperature remains constant. Does that make sense? And as we melt or freeze a substance, we call this the heat of fusion. Oh, sorry. Or the enthalpy change of fusion. And we kind of dealt with this last unit. but the enthalpy heat of fusion definition, let's just define that right now, is the amount of heat required to melt and what if we're going from liquid to solid, we're freezing it, then what?
Melt or freeze.
Well, in this case, it's a negative, right? If we're melting, we're taking, no. Sorry, that's positive. We're taking in the energy, right, to melt it. When we're freezing it, we're exiting the energy, so it's exothermic. So it's a negative delta H of fusion when we are freezing. But it's the same value for that substance. And fortunately, we don't have to, I guess we could calculate this, but you're going to either ask to calculate this or you'll be given this and you'll find out how much heat is required to do something. Are we good? So we talked about vaporization, condensation. And I guess I forgot to talk about heat of vaporization. So to change a substance from liquid to a gas or gas to a liquid is called heat of vaporization. I'll just add that right here. Is the amount of heat required to vaporize a liquid. And if it was going the other way from gas to a liquid, then it would be what? Gas to liquid would be a negative, right? Yeah.
Wait, so it's delta H. So is there a delta H of vaporization?
Oh, sorry. Yeah. Uh-huh.
And that's positive or negative?
So it depends on which way you're going. So think about where the heat's going from. If you're going from liquid to gas, what do you have to do to liquid? You have to take in the heat, right? So it's endothermic. But if you're going negative heat of vaporization,
Condensation would be negative.
that is condensation. Yes.
Positive.
Yep. So just think about where the heat's going. If it's going in the system, then it's positive. If it's going out of the system, it's negative. We good there? So the last one is not real common. Sublimation. Anybody know what sublimation is? Phase from solid directly to a gas. What's an example of that? Dry ice. So like dry ice. Dry ice is solid carbon dioxide, and then you give it energy, and it changes to carbon dioxide as a gas. So if we want to know the delta H of sublimation, that's equal to the heat of fusion plus the heat of vaporization, because it's doing everything all at one point. Does that kind of make sense?
So is it delta H of fusion, delta H of vaporization?
Yeah. Yeah, whoops, sorry. I'm sorry. Okay, all of that for this. Here we go. You ready? Or do you have any questions up to this point?
Wait, where did the fusion come from?
Heat of fusion, that's melting or freezing,
Oh,
depending on which way you're going. So generally, if we melt it, if we go hotter, then it's a positive value. If we go colder, it's a negative value. But sublimation is going from cold to hot, right? So if we have sublimation, then it's equal to negative or positive delta H fusion plus positive delta H vaporization. And the last one is deposition. And this is phase change from
gosh.
gas to a solid.
What's an example of
Great question. I'm glad you asked. Well, last weekend? Last weekend I went camping with a bunch of boys. We just roughed it. You guys ever go camping out without a camper? It's just without a tent, with just a sleep bag on the floor, on the ground? Well, it was up in the mountains and it gets cold, right? Well, in the morning, then the outside of my sleeping bag was wet. No, I didn't wet my pants. So it was wet because of the dew, right? Well, how did it get there? It went straight from a gas. Well, it didn't go to a solid, did it? Hold on. That's not it. Oh, so sorry, that was a bad example. Rewind. Here's where it is. So you park your car at night, and everything's dry and wonderful. And then you go to bed and you wake up in the morning and you have to scrape off your windows, right? There you go. That's going from a gaseous water to solid ice. That's deposition. So it deposits our ice on our windshield. Same thing, just not as cold when I'm camping, hopefully. Okay, sorry. We good? All right, so let's talk about heating and cooling curve. And this kind of sums up everything we just barely talked about. So on the y-axis, this is the temperature, and it increases going this way. And on the x-axis, this is heat energy. You guys get that there's a difference there, right? Heat energy is measured in joules. Temperature is measured in degrees Celsius or Kelvin. Okay. So it's going to look something like this. So if we're talking about water, what's this value? 0 degrees Celsius, and this value right here is 100 degrees Celsius. So this is solid ice, okay? And you can, as you increase the temperature of that ice will increase, directly related, right? Until you get to the melting point of ice, which is 0 degrees Celsius at sea level. Then you keep giving it energy, and it stays the same temperature. So the temperature remains constant, like we mentioned. And then as you keep heating it, now it's all liquid, and it changes the temperature of the liquid directly related to the amount of heat you give it. And then as you reach the boiling point, then it stays that boiling point, 100 degrees Celsius at sea level, until you reach a gas phase. And then once it's all gas, then you can continue to increase the temperature as you give it energy. Does that make sense? So how do we figure out how much heat is required to boil? You go up in the mountain to go camping, do your rough trip, and man, you want some hot cocoa or coffee or whatever, right? So you take a snowball and you put it on the fire in a pan and you boil it, right? First you have to melt it. First you have to bring that ice to 0 degrees, and then you melt it, and then you heat the water up until it gets hot enough to drink. Maybe what, 70 degrees? Who knows? So how much heat is required to go from maybe -4 degrees Celsius to 70 degrees Celsius? We can do this. This has a change in temperature. So what equation do we use for change in temperature? MC delta T. You with me? Same thing here. MC delta T. What's the difference between this one over here and this one over here? They have a different specific heat capacity. One's for ice and one's for liquid water. And we will be given those things. Okay? How do you find the Q here? This one's delta heat of fusion times the mass. Or is it mass or is it moles? Let's see. It's per mole times the number of moles you have. So you have to convert grams into moles and then use this value. So whatever you do, make sure you look at the units to make sure they all cancel out, right? Same as everything. And then this one right here would be Q equals delta H of vaporization times the number of moles. And then right here, if you was going to go into a higher temperature of gas, then you'd use Q equals MC delta T again. And the specific heat capacity of a gas is different than of ice and water or liquid. So how do you find the total heat? Do all those equations and add them all up. Does that make sense?
Can you explain the ice and solid? Like,
So right here,
or where you wrote ice and where you wrote solid on either side of the diagonal?
okay, this is in the solid phase, so ice. This is in the liquid phase, so water, and this is in the gas phase, so steam. And right here is where it transitions from solid to liquid. Here it transitions from liquid to gas.
So the flats are transition phases.
Yep.
The transition phases where we have the fusion.
And how do we know we don't use this? Right here,
Because we're at freezing?
we don't have a change in temperature.
Right.
Yeah, it stays the same temperature, so we're not going to use that. So we got to use the heat of fusion and heat of vaporization. Good? Okay, should we do an example? And you will have one of these on the exam. You might not have one this in depth. I'm going to do the biggest that you can have, and then, all right. So let's do an example. How much heat is required to convert 135 grams of ice at negative 15 degrees Celsius to 120 degrees, or to vapor at 120 degrees Celsius. So step one, first of all, we have to know the heat of fusion, heat of vaporization, specific heat of the different substances. So let me just give you these real quick. So for H2O, we have delta heat of fusion is 6.02 kilojoules per mole. Heat of vaporization is 40.79 kilojoules per mole. The specific heat capacity of ice is 2.09 joules per gram degrees Celsius. Specific heat capacity of water, anybody know this yet? 184, we'll just say 18 joules per gram degrees Celsius. And specific heat of steam is 2.03 joules per gram degrees Celsius. Okay, now we're just going to use, maybe picture that in our mind. Our first step, we're in the solid phase, negative 15, we're down here somewhere. So we're changing temperature, therefore we use Q equals MC of ice delta T. Well, we have 135 grams. Any questions so far?
Your C values, C of ice, C of water, is that right?
C of ice, C of water, C of steam. Yep. Or a solid liquid gas. So this Q is going to be 135 grams multiply specific heat capacity of ice is 2.09 joules per gram degrees Celsius. And what's the change in temperature? It's only 15. Because once we get to 0, then we have to use heat of fusion. Does that make sense? So it's going to be 15 degrees Celsius. Is it going to be positive or negative? Oh, nuts. Dang it. $135 grams, 2.09 joules per gram degrees Celsius, and 15 degrees Celsius. Is that positive 15 or negative 15? Positive, because we do final minus initial. 0 minus a negative 15 is positive 15, right? And so we get this is so when we do this, we're going to get 4,230 joules, right? Make sure we include our units, guys. When we use the heat of fusion, heat of vaporization, it uses kilojoules. When we add these together, they better be in the same units. So since these are kilojoules, I can either go to kilojoules or go to joules. What would you rather? Kilojoules, because this is pretty much 4.23 kilojoules, right? So just make sure your units are the same. Otherwise, you'll get an answer, I know I did that right. But you've got to make sure they're the same units. Okay, so that's our first step. Q2, so this is Q1 going from solid ice to start melting to 0 degrees. Now we're going to use this delta H of fusion times the number of moles. So that means we got to convert grams into moles. So let's do that down here. 135 grams of H2O has a molar mass of 18.02 grams to 1 mole of H2O. And we get 7.49 moles. Don't just plug in 135 grams. If you're always using your units, you'll catch yourself. So heat of fusion is 6.02 kilojoules per mole. Multiply 7.49 moles. And we can see our moles go away. And we will get 45.09 kilojoules.
So basically you're saying just like convert the units to everything to kilojoules and everything to moles.
Yep. Not everything, just for heat of fusion, heat of vaporization. Because when we use this formula, it's mass. So we do want that in grams, because we could see the grams here cancel with grams there. Degrees Celsius with degrees Celsius there, and we get joules. So we got joules, we got to convert that to kilojoules, or convert everything to joules. Doesn't matter. But since these are going to be huge numbers, it's going to be easier to convert it to kilojoules. Then you're going to have smaller numbers to deal with. Good? Do you get this process? You do that until you're all done, and we'll get a final answer. But so Q3. So that is going from, so this was Q2. Now we're doing Q3. We're changing temperature of our liquid water. So we're going to use MC of water delta T. We still have a mass of 135 grams. This time it's 4.18 joules per gram degrees Celsius. Times the change in temperature is what? Now we're in the liquid phase. Change in temperature is from here to here. Do we need to know that?
Yes.
The answer is 100 degrees unless they tell you something else, right? Maybe it's a different substance, then it's not 100, right? Then we would have to give you the melting point and boiling point. But does everybody know the melting point of water is 0 degrees Celsius? Boiling point is 100 degrees Celsius. So this is 100 degrees, and again it's from 100 final minus initial, 100 minus 0, so it's a positive 100 degrees. We do that math and it's 56.48 kilojoules. And then Q4 is going to be turning our liquid water into gas, heat of vaporization, which is heat of vaporization times the number of moles. And that's equal to 40.79 kilojoules per mole times 7.49 moles. And we get 305.52 kilojoules. Kind of a long process, right? And this is going to be the biggest one ever. I won't have you do one longer than this. But most likely it'll be going from a negative temperature to maybe 50 degree water, right? And then the last step, Q5, That's gonna be changing our temperature from 100 degrees Celsius to 120 degrees Celsius. Since we're changing temperature, then it's gonna be M, C of steam, delta T. Mass is still 135 grams. C is now 2.03 joules per gram degree Celsius. And the change in temperature is 20 degrees Celsius. Everything cancels except for the joules. Convert that to kilojoules when we're done, and it's 5.48 kilojoules. How I feeling? Kind of a long process, but do you feel like it makes sense in your mind, what we're doing? So, yes, yep. So our total heat required, you add these up together and you get 416.8 kilojoules. So the big key here is don't forget to make sure they're in the same unit. You go through all that work and you still get the wrong answer because it's not the same unit. Okay? All right. Sorry I went a little over. More next time. Any questions? Oh, hold. Do you want me to give you another one of these? Here's another worksheet. Mike, do you want this? That's the one, so 9.22 is huge. We didn't finish that one, but good start anyway. Thank you. Yep.